All right. Okay. So we are back. So today, if you remember, so we are focusing on baby GPT. We're leading up to it, right? So that's going to be the last thing I'll do today is baby GPT. Um, so here's the code. I'm gonna close this one and click on this. So we've started going through some of these materials. We've gone through a lot of this already, dot products, matrix multiplications, the attention mechanism. It's already covered. Um, so that's done. And then here have the description on the baby GPT. But before we get to that, we have to cover something called masks. So that's kind of a very important concept. It's something that we need to look at, what's happening. And then from there, we're going to look at the tick token library and just go from there. So that takes us to this Jupyter notebook here, which is where I kind of left off. Okay. So if you remember, we covered all of this, attention, concatenating the heads, the feed forward, and this is where we are, the mask. Okay. So I'm going to open up just Colab so that we can run the code and make sure we can look at the dimensions and everything. I'm still just using random data for a lot of this, right? So that we can see the actual tensor operations. Okay, so that's, the notebook. All right, so we're going to talk about masks, right? I'm going to switch to the whiteboard just for a second here. Kind of give you an intuition of how this works. So I'll start actually with a simpler concept, which is that of the BERT models and the encoder models. And then we're going to lead into the GPT model, okay? Because I think the BERT models is actually more intuitive than the other one, but we'll take a look here. Sorry. It's like I feel like this is just a random thing. See if I'm looking. Anyway, it's working now. This stresses me out so much. All right. Okay, so let's talk about masks, right? So we're talking about large language models, which are transformers. You should understand what they are. So transformers, they actually had an encoder and a decoder, and you'll see that in the Vaswani paper. And so essentially, you guys know that everything is about tensors, right? So this is a tensor, and the tensor goes into the model, and another tensor would come out, right? So this is another tensor that would come out, and then another tensor on this end would go in, and here, yet another tensor would come out. So in the original transformer, because it was for translation, actually. So let's say they were translating from English to German, right? So English would come in, German would come in, Uh, and then let's see, German would come out over here, right? This is how you would train the model, right? And so, and the connection was here. This would also go into the model, the encoded version. So that was the original transformer for language translation. Okay, but the key thing is there's just a tensor that goes in, tensor that goes out. You know, there's basically tensors going in and out of all these neural networks. Over time, they started doing research on these things. This is the Vaswani papers, like this architecture. And they essentially split this into two things. So we have the encoder part, so this one. So actually, let me do it like this. They split it like that. They split it like that. And this became the encoders, and this became the decoders. All right, so decoders are GPTs. GPTs. So essentially, you can think of it as language would go in, language would go out. But here, the encoder, language would go in, but what would come out here was not language. It was embeddings. Embeddings, that's what came out. So like the embedding. So it's just a transformation of whatever input would go in into something here. And so they didn't quite know how to use it initially, right? Because the whole purpose of this, when they did the original paper, was that this would feed into here. But they decided to split it up, okay? And so this is what we use for GPTs. This is what they were like, what do we use this for, right? And so interestingly, they just decided to create these models called BERTs. BERTs. And then GPTs. So BERTs are bidirectional. So what that means is if you have a sentence, this is a sentence, and you look at this word, to predict this word, you can look in that direction or that direction. Do you see that? So you look at the context around you, in front, sorry, not in front, but to the left or to the right. You see that? So that's, why did they do that? I don't know. They started with that. That was the original idea. But it's, I think they were just doing research and they started with that. GPTs, on the other hand, are in only one direction. They should, you know, they're supposed to predict like the future. So if you have a sentence and you're here, you can only look in that direction because essentially what you're trying to do is predict the future. Do you guys see that? That's the difference between these things. So eventually they took the BERT model and they just, the encoder, and that, you know, remember it was like this. So text would go in, you know, a tensor, and then an embedding was coming out. But then they changed that so that the embedding would map out back to text. They added what is called a head, an additional head. All right. So that, remember, it no longer works with the GPT. It's totally independent now. And they're using it. So they're like, okay, great. We have this thing based on an encoder. And by the way, the encoder and the decoder are like literally the same thing. Blocks, every block has attentions, feed forward layers. Essentially, they're like almost the same thing, with the difference that this one would take in the embeddings from that come from the encoder. But it's essentially the same operation. But we can ignore this now because we're not talking about the translation transformer. We're separating these out into either encoder or decoder. Make sense? So now what I have is, they said, okay, we have this BERT, let's call it BERT, bidirectional, and I forget the transformer or something. And so text would come in here. This was initially meant to just produce an embedding to be used by the decoder, but they're smart, right? They're like, well, that's just a tensor. If we multiply it times another weight matrix, and then now change the dimension to be vocabulary, we can predict words. Okay. So then this became text. So the question that began, it became, okay, so we got text here and we got text. What text do we put? What how do we train this? And so essentially, let's just keep this simple. Let's just put in the same sentence as input and output. Do you see that? And that's where I'm going with this thing of masks, because this should be simpler to understand, right? So now you have, I'll do an example here, cat, the cat sleeps. And this would go into the BERT. And out would, should come out the cat sleeps, right? That's kind of the idea. But they're like, okay, so how is that useful? That's not really useful if you have the same sentence as input and output. And so then they decided, okay, what if we mask some of the words randomly? And so that's what they did. So when we train the model, we're going to provide a mask like this. Or actually, it should be the opposite of that. So what do you think that means? So now they were trying to figure out, okay, um, let's predict that missing word. Do you guys see that? So that's essentially the idea of a BERT model. You would mask, it would then predict, you have here the real thing, so the cat sleeps, it would predict the car. Obviously, that's wrong, right? And so then it would predict, some other word until it got it correct. And remember that as this is happening, the weights in this model are being trained. Do you guys understand? It's a very simple thing, right? That it was doing. You have to think how they logically went about this. They looked at the translation paper, very exciting, very interesting. But let's just focus on this encoder part. This seems pretty fascinating to us. All right, so they build the architecture and they're like, okay, we feed a sentence as input and output, but it's the same. So how do we use that, right? How is that relevant? And so, what they decided to do is let's randomly hide some words and then have the model learn to predict that. So we've all done this in our lives, right? Since the first grade, we've all done like fill in the blank, right? Or the second grade or whatever it is. Some word is missing and we would put it in there. How do we know how to fill it in? You see that? Because we studied, right? Because we have a large language model type of thing going on in our brains, right? And so that's initially what they did. Yeah, go ahead. Well, autocorrect existed before large language models. So autocorrect has been around for a long time, I think. And there are other methods to solve this problem based on like probabilities, like Bayesian methods or something like that. Would this help improve autocorrect? I would go with the GPT probably, but BERT models are, ChatGPT is not based on a BERT. It's based on a GPT. But people have used the BERTs have their use cases, right? They're meant to be like for understanding. So one use case of BERT is BERT scoring, for instance, like that I can give you that's useful. So what is that? Let's say that you want to build a company that has to do with education, right? And your goal is that you're going to create a grader, a fully automated grader. Okay. So then what you do is you build a BERT, text goes in here, right? You guys agree? The cat is sleeping. And the BERT model learned in the example I was giving you to fill in the blank, correct? Fill in the blank. But before that, I said that really initially what it would produce is an embedding, right? An embedding. So what you do is you get rid of this head or layer and put in a neural network layer, right? A normal feed forward layer, and then have that feed forward layer just predict one value. So it becomes like a regression machine. So why is this useful? Because then let's say you're grading homework. So the student gives an answer, blah, 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 and out comes 0.78. And then another student puts in another blah, 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 and out comes out 0.85. It's a grading thing, right? So BERT scores are a classic example of the use of BERT, but they're not for GPTs and things like that. And they have many other applications. Make sense? Yeah. All right. So anyway, so I'm talking about masks, right? Because I think we can all understand that we randomly zero out things, right, with a mask. So I was talking about that. I go back here and I said the cat sleeps. So I give it that string. I can give my computer the string, and instead of running some fancy algorithm or like a sorting algorithm or something like that, which would be very inefficient, right? I just provide an additional tensor of these zeros and ones, indicating which values should be paid attention to and which values should be ignored. Does that make sense? So that's essentially the idea of masks. Okay? So I want to say the cat sleeps. Okay, this is the vector for that. And ignore cat. And now that goes in. So essentially the BERT now takes in the sentence, which is actually complete, and the mask. It uses both of them to know, like if statements almost, right? But the beauty is you don't have to create if statements. You don't have to perform that processing in the CPU. Because remember, what you want to do is run this really fast on the GPU, right? So you give it all the text to the GPU, and the GPU then all it can do is like do matrix multiplications and things like that. So it's easy for it to multiply the words to the mask itself. Yeah, go ahead. It's a CPU task. You said it. It's exactly right. Let's say that so if I hadn't told you this just now, and I just gave you a homework, right, to be cruel, and I said, okay, write the script that, only certain words will go into the LLM. I guarantee you, like 90% of you would come back with like 2 for loops, and you're iterating and you're doing all this stuff, and you can't use for loops in GPUs. Right? That's a CPU task. So you have to do it in another way for the GPU. And so that's why you can imagine, for instance, now you're giving it a batch of sentences, right? A batch of sentences. So this is sentence 1, sentence 2, and these are the tokens, right? So we've established these are tokens. So now you've got, token, token, token for this sentence, like that. And that is what goes into the GPU. But also you need to tell it which one of these for every sentence should be ignored. What's one easy way of doing it? Provide a mask of the exact same value that is something like, do you see that? You see what I'm saying? Does that make sense, guys? So that's what the mask is. There's no mystery. It's for that and that alone. Then all that's left is all like the cool things we do, like the mechanical operations, etc., to get it to do those things. But the goal is this: to not use if statements, to not use sorting algorithms or any of that. Instead, efficiently provide to the GPU itself something that a matrix multiplication can handle. Remember, I've said this before, right? The thing that's hard sometimes about modern deep learning algorithms is that if they were written for the CPU with for loops and the way that we're used to seeing things, it would be pretty easy to understand. It's really those tensor operations in there that are sometimes very difficult. There's a broadcasting in there that solves a lot of problems, but that's a tensor operation. So, there are lots of techniques and algorithms that can be converted to like tensor operations that can be solved by a matrix multiplication, because that way it's pretty fast on the GPU. Got it? Everyone with me so far? All right. So why did I start with BERT? Because I wanted to start with the easier concept to visualize. We all understand that we're just randomly putting zeros and ones. I think for the BERT was like a 15% randomization. So 15% of the tokens were randomized because you have to give the language model enough data to understand what's going on. So it was getting 85% of the data, and it would need to predict the remaining 15% of the fill in the blank. Do you have a question?
Just like that's random. Is it ever just get a complete sentence? Like with the data, do you ever?
Oh, I think, yeah, that's a good question. I think that would be a waste, maybe.
Yeah.
But I've never thought of that. So that's interesting. Like out of 10, 2 should be complete sentences just because that's better for training. That's the kind of thing that I'm sure experimentally they tried and they might have an answer for that, but I don't know it. Yeah. All right. So we talked about encoders, right? I talked about this one. It uses a mask, right? I've stated that. This mask has to be created, right, when you're training. Every time because obviously you're picking random values. The GPT side also uses a mask, but that one does not have to be created differently every time. It's almost like a constant. Okay? And I'll show you what the point is. It's very might take a little bit to understand, but it's very interesting. It's still the same idea of blocking certain things. The LLM should not look at certain things. Okay? But it's a little bit different here. Now, remember the GPT, what's it trying to do? It is like an autocomplete tool, right? The GPT is, I give it a question, it should give me the answer. I give it some sentence, it should continue it. I give it a storyline, it should just continue generating. That's what it does. So essentially, the key thing in the GPT is that it should not see the future, right? It should not see the future. And so the mask for the GPT looks like this. Yeah, I think. Yeah, sorry. But you get the idea. So zeros above the diagonal. Do you see that? So it's like a this is the diagonal. Everything underneath it is ones, and everything over it is zeros. And that's the mask. Why? Well, because, let me do a simpler example here. I'm going to do the cat is sleeping. Oops. Remember, I'm doing the attention mechanism, right? And that's the other thing I should say. The mask is used in the attention mechanism. Okay. So this is the attention score. What did we know about attention? We've established that if the sequence is 40, then this is 40 by 40. If the sequence is 10, then this is 10 by 10. It's a square matrix, right? Right. And so now I'm going to use the words, although we know it's K and Q, but intuitively we know it's the words. So I'm going to do the cat is sleeping. So we know that the attention will have values for everything. But the problem with that is that meant that if we were at the cat, it could look at sleeping in the future. Do you see that? And learn a value for sleeping in the future. And we don't want that. We all, if we are at the cat is, sleeping should not be included in training because that's cheating. The whole point of the large language model is to learn to predict, not to actually look at the future. And so that's why the matrix, and let me see if I can do this correctly this time. So I'll show you, hopefully, how this works. I'm trying to do this correct this time. And 3 zeros here. It's always like this. And it's almost a constant of length size. So 40 by 40 or whatever it is, right? There's a thing in PyTorch we'll see in a second in the code called the trill, and we can do it with that. Why do we do this? Because when we're doing the cat is, if you notice, there's going to be a wait for this, a wait for that, a wait for that, but no wait here. It can't pay attention to that because the assumption is we're predicting until the cat is, and the next word would be sleeping, but it can't really see it. Do you guys see that? So that's what the mask provides. We give it the data, right, which will be another matrix, and we kind of like add it with this one, and these values need to be zeroed out. Do you see that? So that's the purpose of this mask in the GPT. To prevent it, it's like a causal mask, I think, and it's preventing look ahead. So it never can calculate a weight for values that are in its future of the sentence. Yeah, go ahead, please. Pardon? Preventing it from seeing words in the future. So before we were blocking certain words that it had to learn how to predict, right? Randomly. Here it's learning how to predict, when we're training this model, we would give it the cat is, and then we want to learn the word sleeping. So it shouldn't look at future words. It's almost like this controls where we're at, and this controls then what comes after. Yeah, go ahead. Yeah. No, it's not random. Yeah, exactly. No, so I said I was actually making a contrast, right? That we have a transformer. So yeah, I'll repeat, right? So initially there was a transformer that had an encoder and a decoder, and that was for translation and work together. But then one became the BERT model, and one became the GPT model. Both used masks. The BERT model, I gave the example, had a mask where the same sentence would go in and here and come out here, but we would mask some of these by randomly zeroing them out. And essentially the model would learn to fill in the blank. Does that make sense? Those were random. The GPT does not have that goal. The GPT has the goal of predicting a term in the future. So now so BERT would work like this. The blank is sleeping. But it can look at this and that to answer this question. Do you see that? And we would just randomly pick which ones we wanted to filter out. The GPT is more strict, if you will. What the GPT does is it never looks at the future. Right? It can only look at the past. I can't, how is the stock market, how is NVIDIA doing in the stock market? It's doing great. I can't give it that, right? I can only give it, how is NVIDIA doing in the stock market today? Great. You see, so I'm giving it the thing that it's supposed to predict. So it can't look at the future. All right. So a GPT does, so in this example, it would be the cat is blank. It's predicting the next term. Okay? So that's what we're trying to mask. So essentially, instead of we create a mask similar to the previous one, but the ones and zeros are not random anymore. They actually always follow this trill pattern because amazingly, this controls that they will never look at the future. When this sentence compares itself to this sentence, if it's here, it can never look and know what these words are. They're going to be blanked out. You see that? Yes. So you can assume like if it's here, it's the, right? So the can only look at itself and nothing else. Right? And that's the training that happened there. When I'm talking about the cat, it can only look at the cat, but not is sleeping. So these values they're not included in the optimization. They're just zero. So nothing in the weights happens. Do you see that? The only things that happen to the weights of the LLM relate to these ones. Because remember, these ones are just mean what? That you can calculate a weight for it. Right? The actual value, we'll see this in the code, was 0.20, 0.3, or whatever. But here, even if it had been 0.70, what's going to happen to it? It becomes zero. It's zeroed out. And so that's how it works. So if the LLM is currently looking at, if the LLM is currently looking at this sentence, the cat is, it can only calculate weights for this, but even if it calculated one here, there's a zero there. So that masks it out. So essentially, this solves the problem of never seeing the future. It sees the future in the training, right? Like you give it an input, it predicts, it compares to the real, and it back propagates. That is true, but it can't look at the data in here. So another way of saying this is that when we train the model, right? Maybe another intuition is this, which is complicated to visualize probably because we don't think in terms of the GPU, right? It's not efficient to just, do a for loop and just say, okay, the cat is. I know that I'm here. I should not give it sleeping. That's not efficient. What's more efficient is to give the GPU the cat is sleeping. So the GPU gets the whole sentence, but the solution is to use a mask to zero it out at the same time. So it's almost like, imagine if I went to you guys, hey, here's the answers to the exam, and then I do this. So the answers, I'm showing them to you, but they're behind the mask. So now you don't see them. That's it. That's actually like what's happening. So the GPU gets the answers and the mask, and I'm blocking it. So it doesn't actually see it. And that's actually way more efficient than a whole bunch of for loops to extract it and so on and so forth. Got it? Yeah, go ahead. Well, this is about, so the mask looks like that has this trill shape of ones, and, over here and zeros here, so that it doesn't look at the future, the next word, wherever you are. So like I said, if you're the cat is, then remember that we apply this in the attention scores, exactly in that 40 by 40. And what are we learning there? Remember the example of bank and bank of the river and all that? So that's what we wanted to pay attention to, but we also don't want it, if it's at the bank is closed, we don't want it to see today or is closed and customers, if it hasn't actually gotten to that part of the sentence. So that's how this controls that. Yeah, good. Well, it's you don't want to, so you're giving it all the text, but that wouldn't be helpful because it needs to learn to predict the next word. You see what I'm saying? So it's more efficient to give it, as I said, all the text and just block it. And then it's going to learn, it has to adjust the weights. The weights themselves are the ones that will predict those values. Because what happens is you give it an input, predicts an output, which is wrong initially probably, but it compares to the actual real data, right? And then it back propagates the weights until it does a good job there. The problem is in the attention mechanism, it's got all the data. So you need to mask it out a little bit. And the way that we're masking this here is because it's not like the BERT where we fill in the blank. Here we want to predict the next word. Do you guys see that? We'll see this in the code in a minute. So hopefully that'll become more clear. But that's the concept essentially. All right. So let's go. Yeah, go ahead, please. Yeah, please. See, that's a really good question. So the mask is going to be in there. It doesn't go away. So once you train the model, the mask will be there. So so there won't be any weights in the top part of the attention scores. So remember that during training, what you do is you feed it tons and tons of sentences, which are actually embeddings, and it's comparing all of them, right? And so it will learn a set of weights here. These are weights. Now you're done training, this is still there. What's going to happen is you have some text. This text should be converted into embeddings. And then that goes here and here via KQV. And it's going to then, those values are going to be multiplied with whatever you had in here already. And then it's going to like activate certain connections in here that give it the context that it needs. Yeah. Yeah. Mhm. You feed it the sentence, yeah, the text. Well, I think if you're trying to predict sleeping, then you would feed it the cat is. No, because as I said, the attention mechanism is already zeros here, and this is just weights. So this is just, you feed it massive amounts of data, right? And there's multiple attention heads also, right? And so these are all transformations. So think about it, text to embedding, right? And then for that sentence, and then that embedding becomes Q and K, right? But multiplied by whatever weights you learn there. So remember, it's just a matrix multiplication always. Do you see that? And so that matrix multiplication here is just this with these and this with these. Sorry, it should be right. So we did this QK, right? So it's just a matrix multiplication of that. Here we do have weights, WQ and WK. So I guess the magic of this is that it learned that going to that example of the bank and the robbers. So it's somehow going to conclude the bank and the robbers. That's the goal of it. So it should do something like this, where this and that has a high value here. But these should remain zero values because if you're just the bank, it would not be able to predict the robbers here. That, it can't look at that in the future. You see that? So, but yeah, so essentially that's what's happening with all the matrix multiplications. Let's take a look at the example in the code and let's see how that goes. All right, so let's try this with a visualization. Okay, so let's do the mask here. All right, so I'm going to use Colab. And I think I'm going to, all right, so we have this. So I'm going to do a tensor torch ones 10 by 10. This represents, it should be 40 by 40, right? If it was the attention score. So a sequence of 40, right? So here we're doing torch 10 by 10, but it's going to be a trill example. And I think I need to add torch to this. So let's do import torch. All right. So now let's run this one. Okay, so it's 10 by 10. And we can look at it, the trill definition. So that's essentially the mask. Okay, so remember, it is in the context of the words, right? So we're not filling in the blank. The model is learning to predict into the future, right? So we have ones and zeros there. Now let's assume an attentions. We'll have to randomly create an attention score. Let's do this one here. I'm going to say n equal 32, for instance. Okay, so I'm creating here size 10 attention, which is a random tensor of n by 10 by 10, right? So what does this represent? This represents the result of K matrix multiplication Q, right? So what we talked about last week. K matrix multiplication Q, okay? So we've learned that we perform this operation, okay? And it's supposed to represent a sentence like the bank where the robbers went, the bank where the robbers were. And then as the model is training, it should learn to pay it, like bank and robbers. That becomes important. Or if we're talking about the bank and it's a slippery sandy area, okay, then bank and sandy, that connection becomes important. And that provides the context that you need to know what you're talking about. Am I talking about the bank institution or the bank of the river? All of that is still the same. The only thing that changes here is that now we're going to have this mask that's triangular like that, so it can't look at words in the future, essentially. You know, the sentence that you're comparing. Okay. Another way of saying this maybe is like this. If I leave all these values as one, it'll be good here, but it'll be very bad at predicting the next word. When I actually try to get it to predict that next word, it's not going to be good at that because the weights were not trained for that. This forces that issue. This forces that the thing that it's good at, it's predicting the next word because it's never looked at it, right? So when we're doing the training, you know, it has to predict a word that matches the real word. Okay. And if it doesn't do that, it's not going to be good at predicting. So that's why this helps. All right. So let's take a look here. So I have that. Now let's see what the trill will do. We're going to mask the attention score. So this is what the trill will look like, and this is the attention scores. So the trill definition is 10 by 10. Okay, now let's take a look at this operation. So this is just like an if statement. So I'm saying if the value is 0, return true. If the value is not 0, return false. So you can see it returns true or false, right? So now what I'm going to do is show you the operation where you apply the mask to the attention. So that's this. Okay, so here I have size 10 attention, right? What is that? That's this tensor here, okay? And this tensor should represent like the weights of the attention matrix. And then I have this mask, which looks like this trill. So now I'm saying size 10 attention dot mask fill, applying the mask to it, and wherever the value is true, I'm going to change it to minus infinity, okay? So I'm going to do that here. Okay, so that's been applied. And now what I'm going to do is I'm going to print it. Now notice this batch has 32. What does the 32 represent here? 32 sentences, correct? And each one has an attention score. For each sentence, you have an attention score. So what I'm going to do is I'm only going to print one masked attention now. Okay, I could print 0, 7, whatever it is, 5. I'm just doing one of the 32. Okay, one of the in the batch. Do you see that there? So what I did is now maybe you start to see what's going on, right? So what's at the bottom? There's actually random values in there. What do those random values represent? They represent weights that are learned, right? In that sentence that's happening there. So it represents that the cat is sleeping on the bed. The cat is sleeping on the bed. And look at this value here, 0.39, right? That's a high value. So it's saying that this one and that one over there are maybe highly correlated. Do you see that? But it only looks at this down part here, not at the top part here. Okay, because it's never able to look at the future, right? That's essentially what's happening there. So maybe the question that you had before is that these values are computed by So they don't exist there. They will be computed and appear there as you give it the sentence. So maybe this is how I can answer your question. So you gave me this example of the cat is sleeping, right? Well, when the cat is sleeping and the cat is sleeping, the weight multiplications and everything that happens would fill in these values. Do you see that? So that's what I can say, because obviously there's, these values will appear there. So if I just, they're the product of a K and a Q. Do you see what I'm saying? So X comes in, becomes K and Q, do that matrix multiplication, that appears. It's not like these values were here and then the cat is sleeping came in, you matrix multiply them and something else became real. Do you see that? In fact, these values are computed in real time. That's exactly how it's happening, because we can work through it. We can work through the problem. Like, we know the math, right? That's the beauty of knowing the math. You guys tell me if I'm wrong. Let's go with it. I have X. I know that's the sentence, whether it's a batch of 32 or just one. It's numbers in X. Okay, great. I do know that there's a matrix multiplication here. WK, correct? That becomes K. This I know where it's coming from. These are weights in the neural network. Do you guys agree? Learned. These are learned. This is the whatever comes from the sentence that the user asks the question. Becomes K. Q is WQ. What is WQ? Another weight matrix that was learned by the model. X is whatever came from the user and becomes Q. So what's the next operation? KQ. There is no other value. And what does that produce? We already know 40 by 40. But zeros here, nothing there. Only values here, and those values are important to know, to provide the context of what to pay attention to. Do you guys see that? So that's essentially the idea. All right. So now let's go back to the, oh yeah, go ahead, please. Do you want me to go back to the whiteboard? Okay, hold on. Did I just hit N? I'm afraid I'm gonna, nope. Oh, I think I'm just kind of like in the middle of it. Yes.
Oh, yeah.
Mm-hmm.
Well, we had
Yes. Mm-hmm. The sequence is 10. Every sentence is defined by a sequence of 10. Yeah, or tokens, yeah. Yeah, I'm not using 40 because 40 is too big. I'm using 10 just so we can visualize it better. The second 10, let me see if let me go back to the whiteboard to make sure I understand. So that's 32 sentences, each one having an attention for that sentence.
Yeah, so 32 one.
32 sentences is about, so 32 10 tokens and an embedding of 512 or 64, right?
Yeah,
that's what comes in. Okay, so the attention is 10 by 10. Okay. And what's the question? I'm sorry.
so, yeah.
Right. So that's attention 0.
Yeah.
That's, if you looked at it, that was just one 10 by 10 for one sentence. It's the attention scores. So that's the thing I've been drawing. The cat is sleeping. So the cat is sleeping or sleep. The cat is sleeping. That's what 10 by 10 is. So it compares that sentence to itself. There's 32 sentences, and each of the 32 sentences has its own attention and its own mask. We're using, this is not actually X. This is actually K and Q. But that's the same as, does that make sense? So yeah, so because what happens is, see, think of it this way. There are 32, 10, 5, 12 initially, right? But it's really just for each one that you're doing this. So it's 10 by 10 things where each one is a word, the or whatever, but they're actually represented by vectors of 512. So this is a vector of 512. This is a vector of 512. So when I perform that matrix multiplication or the dot product, they're the same size. If I make them of 64, they can still be dot product. So like 10, 10, right? So I always use the word the cat to be more intuitive. But these are not actually words. What do we know? We know that the is a vector of 512. And so is cat. Cat is a vector of 512. So now I can do, let's say that I have cat over here is sleeping. So I want to do an operation between these two that results in just one value. Well, what can I do? Well, quite simply, this is a vector of 512, and this is a vector of 512. So if I just do the dot product, the first operation that we did, what do you get? One value. So we give it that ability to do that. But the value that it calculates is dependent upon the training and the weights. So that's why, these are all transformations of what's going on in here from X and the weights WQ to give us. So it's like almost like X is a vector of 512, right? And then there's a weight Q. And for just one token, it might make it 64. Oops, sorry, 64. And that's your Q. But also X, the same X at 512 with a matrix, a weights matrix of K just transforms that vector of 512 to a vector of 64, which is Q also, sorry, K. This is K. And then when I do this, I always say QK. But I'm essentially saying, if I draw it over here, this vector of 64 and that vector of 64, if I take the dot product of them, it's one value. Does that make sense now? Yeah. Yeah. So that's the key intuition, right? That you're doing that operation. Now, the values here are random and don't become meaningful until we've done all the training. And the weights of this one and this one are the correct ones. Okay. And what results is, so think of it this way, how do you know that it's going to get good values? Because we have an objective to predict correctly, right? So we're training. If it's just predicting randomly, then these values are random. They're just random values. But when do they become good? When you ask it a question, hey, how's NVIDIA going to do tomorrow in the stock market? And it does all these operations and it looks at the weights here, or it looks at the weights, sorry, here to produce values here, right? To pay attention, NVIDIA stock market, something like that. Okay. And I say, so I asked the question, how is NVIDIA going to do? And I say, cat is blue or some. That's what do I say then? That's bad. But what produced cat is blue? The values in here that were computed by these weight matrices. So what happens then? It keeps doing that. How's NVIDIA going to do tomorrow in the stock market? Computer black green. Why was that produced like that? Because these values are random, right? It calculates this KQ, these vectors get dot product. This value was not meaningful. Now think about it after thousands of iterations, massive amounts of data. How is the stock market going to do tomorrow? NVIDIA, and how is NVIDIA going to do tomorrow in the stock market? The stock will go up by 0.5%. And I'm like, I like this answer. And how did I get that answer? Because these weights were meaningful, which meant that it took the original X, made a matrix multiplication, created K and Q, and then this vector K and this vector Q did a dot product to produce a value, and that value was useful for the next step in the prediction. Do you guys see that? That's essentially what's going on. Okay. All right. So yeah. But anyway, that's what the mask, actually, all of this we had talked about before. The thing that we hadn't talked about before is that the mask will have 0 values here so that there's no values here because we want to force the model to not know the future, essentially. And that's what, just like before, we would fill in the blank and randomly select once. Now we just select once so that if where the cat is, it can't see sleeping. It can't make a connection to that because it's not. You see that? So that's essentially the idea. Okay. So let's take a look at the code. So we can go back to the code. And what time is it, by the way? So it's 8:10. We started at 6:30, 7:30, 7:50. So we're 20 minutes over. So let's take a 10-minute break right now until 8:20, and then we'll finish up. All right.